We've got a parallel plate capacitor with circular plates, and it's got this voltage difference. Now we're trying to find the B max at the radius of R. And so what we need to do is use Maxwell's fourth equation. So that would be the magnetic field, Ampere Maxwell thing. B dotted with ds is going to be equal to mu naught I enclosed plus mu naught epsilon naught and the time derivative of the electric flux. Well, essentially what they're asking is at 2 pi r, if we make a little circle around here at 2 pi r, that's the left side. We're going to set that equal to, well, we don't have any current inside, so we're going to get rid of that. But we do have voltage. And voltage, especially inside of these capacitors, you could represent that as E times the distance between them. So if we divide the voltage by the distance between them, we'll get the electric field. And on this side, we need to get this electric flux situation. We should know that electric flux is equal to electric field times the area that it's in. But we really want the time derivative of that. So we're just basically looking for the derivative of this stuff, keeping in mind that the area is not going to change. So the area is going to stay constant. And so we really just want the derivative of the electricity thing, which is over here, electric field. So we need to figure out this equation over here in order to take the time derivative of this and essentially be the derivative of this. Oh my goodness. Well, let's do that over here. So we got 190 sine of 168 pi t divided by the x, which is going to be 7.2 millimeters. And we really want the time derivative of this because this is supposed to be the electric field. Now, how do we take the derivative of that? It's just going to be, well, what's the derivative of sine? It's cosine. So we'll have the cosine of 168 pi t somewhere. And then we also have to include the constants, 190 divided by 7.2 millimeters. And we also have to multiply by 168 pi. And that's going to be the time derivative of E. Now we're looking for the max, so this stuff's just going to go away. And this is what we're going to plug in for that. So we're going to put mu naught, epsilon naught, and the time derivative of this, which includes the area. So we'll just throw in the area real quick, and then we'll have, and the area is really supposed to be pi r squared. So pi r squared, big one. And then we still have 190 over 7.2 millimeters times 168 pi. And if we divide this whole thing by 2 pi r, then we'll get the B. All right, let's go ahead and grab the calculator. And we're going to say mu naught, that's 4e to the negative 7 times pi. Then there's E naught, so that one. And then there's another pi. And then there's r squared, which is going to be 34 to the negative 3. And then we've got the 190. I'll put the 7.2 down here just to make that a little easier. So we got 190 times 168 pi. And on the bottom, we'll have the 2, the pi, the r, and 7.2 millimeters. Giving us the B max is equal to 2.6 e to the negative 12 Tesla. Ooh.